Okay, let's talk about generating AC voltage. We already talked about that a few minutes ago when we were talking about the STE chapter, but now we're going to do some calculations with it. And one of the places we talk about frequency and wavelength, which is a different idea completely, we need to look at what is the wavelength of a radio station which had a broadcast frequency of 880 kilohertz. And the way we find that is the frequency is 880, so we're going to divide that 300,000, the speed of light basically, by 800, the wavelength. So we're going to divide 300,000 by 880, and that will give us the wavelength. Okay? Now, this doesn't sound like anything you're ever going to use, right? If you take the ham radio class, you might need to convert from frequency to wavelength or wavelength to frequency. And either way, it's the number that you have, 300,000 divided by the number you have will give you the other one. You know what I'm saying? Like if we have, everybody take 340.9 divided, 300,000 divided by 340.9 and tell me what you get. 300,000 divided by 340.9. 880. So if you're going from frequency to wavelength or wavelength to frequency, it doesn't matter. Either one of them, you take the number 300,000 and divide by what you know, and it'll give you the thing you're looking for. Is that pretty simple? Everybody say yes. So now you can find frequency or wavelength, right? So if a radio station is broadcasting at 880 kilohertz, then you can divide 300,000 by the kilohertz, and it will give you the meters of the wavelength. Isn't that handy? And you will find that in a Gordon West FCC radio book also. And you don't have to do those calculations in the radio technician test because that's, I don't think you do. You might, but I don't think you do. I'm not positive. Okay, frequency of a radio wave, if it's a wavelength, is 297 meters. We just take 300,000 divided by 297. Is that correct? Okay. And we'll find 300,000 divided by 297, just as I said, will give us the frequency, and 1010 in kilohertz. In kilohertz. Okay, you're going to wind up in kilohertz. Okay. An AC wave has a maximum value of 100 milliamps. Find the instantaneous current at 70 degrees. That's a sine wave question, remember? What is the sine of 70 degrees? Sine of 70. 0.9397. Okay, so 100 times 0.9397 is going to be 93.97 milliamps. Okay. Instantaneous value, 70 volts at 30 degrees. We did that, didn't we? Half 70 volts, 35 volts. We did that before. Let's see here. Let's go to some of their quizzes. No, I don't want to go to their quizzes. I am going to go through, and so you have these to look at. There's that quiz. There's some more questions on the same one. These are examples. Frequency of a signal whose period is 4 seconds. Okay, we didn't talk about period, but it's in your book. Don't get freaked out about that. It's not a big deal. Peak voltage. Okay, you know how to find peak voltage. Peak is RMS times the sine wave. No, RMS is equal to peak times sine wave. Sine of the angle. Sine of the angle times peak gives you RMS. Remember that. Okay? Now, where are we? Here's a solution. On the video, you can stop it and take a look at that. Let's go to the next example. Time base of AC wave is 10 divisions is set to 1 millisecond per division. What's the frequency? And here we have a solution for that. If you're watching this on the video, you can stop it and take a look. And we do want to talk about phasors. Because vectors are how we solve everything in electrical AC. 22 ohm electric iron is operating at 110 volts, 60 cycle line. A phasor diagram, find the current and power by, well, we don't really care about drawing a phasor. That doesn't help us much. But take a look at that if you like. Now, I'm going to tell you something. This book discusses Pythagorean theorem. Pythagorean theorem is very simple. Hypotenuse squared is equal to adjacent squared plus opposite side squared, right? Very quick and easy, dirty, if you're only looking for a side. But in AC, we're never looking for just one side. We always need to know the angle because we're going to have one triangle that's a result of resistance, inductance, capacitance, things like that. And from that, we're going to get a power triangle. And the only thing they have in common is the angle. So if you just get the solution of one side by Pythagorean theorem, you can't move to the second angle and find anything because you only have the angle and one side. Okay? So we generally don't want to do things by Pythagorean theorem. It's a handy formula. It's easy to use. You can practice it if you'd like. But we're going to do everything in this class with triangles. Okay, find the frequency and go ahead and stop that if you want to look at it while you're at home. 3 more questions. Go ahead and stop that and look at it if you want to at home. And we're not going to get into that too much. We're going to stop this. Let me pause this for a second. And we're rolling, and let's talk about reactance of a coil. We've been talking about that all morning. The primary of a power transformer is connected to a 117 volt line and has an inductance of 150 millihenries. Find the inductive reactance when the frequency is 60. What's the formula? X sub L is 377 times 0.15. Because if we convert back to base units, 150 millihenries is 0.150, right? So 377 times 0.15 is, so our answer should be, what a shock, 56.5 ohms. Shocking, I tell you. Okay, and they use, by the way, the math book likes to use V, that's the electronic symbol for voltage. But we always use E. It always annoys me when I see the V on the things. But anytime, if you see V on a quiz, it's because I didn't catch that I used something out of the math book that still had the V on it. Just assume that that is E instead of V. Okay? So 117 divided by 56.5 ohms is 2.07 amps. That's our answer. And another example of an inductance of a coil in order that it have the frequency reactance of 942 ohms at a frequency of 60. So that's just doing it the other way. We're still going to have X sub L is 377 times H. We don't know what our H is. It's saying what is the inductance of this coil if it has a resistance of 942. So 942 is equal to 377 times L. What is L? Divide both sides by 377 and we find 942 divided by 377. And we're going to find 2.5 is, they rounded it, but 2.498 is much more accurate. Thank you very much. Okay. And series resistance and inductance. Okay. Let's see. We have an X sub L of, we have a resistor of 100 ohms and an inductor with an X sub L of 100 ohms. Connected across a voltage source with a frequency of 60 hertz. The voltage drop across the resistor is 85 volts and the 85 volts across the inductor. Find the total voltage to find everything. This is a really bad solution. They didn't show you how they got here, did they? They don't, do they? Not in this example, but they do in the book. But let's go look at this. And what they're talking about is they have an X sub L. They're moving into triangles already, aren't they? And they have a resistance. And this is 100. And this is 100. And you know that if you've got 100 on this side and 100 on this side, what angle is that? That's a 45-degree angle. So we're moving into, that is a phase angle. So we've got our first phase angle, right? What's the sine of 45 degrees? 0.707, right? So we know the sine of this thing okay. We want to find the hypotenuse. This is called the impedance. And whenever you're working with a circuit, we're moving into a new phase. We no longer have PEIR. Now we have PEIZ, impedance. And impedance, we talked about this very slightly before, that we had resistance. Remember we looked at that coil and I said it has real resistance, DC resistance. That's the resistance down here. And they're saying in this case is 100 ohms. The X sub L, the inductive reactance as a result of the coil, is 100 ohms. Okay? And this is going to be pretty simple because we could do this by Pythagorean theorem, right? 100 squared plus 100 squared. Add that together. Take the square root of that. 141.4 ohms. And that is a total impedance of this circuit we're talking about. So when we're talking about PIEZ, we don't have R down here because it's no longer just resistance. That was in the good old days of just DC with resistive circuits only. Now we're in AC where it might be resistance, inductance, capacitance, and some other things. And so now we have a Z, 141.4. Okay, 41.4. We have a given voltage. I lost it, 85 volts. It's PEIR, sorry. And I want to remind you that if you were doing this with your old PEIR, as long as you write it PEIR, and I'm going to insist that you, whenever you do a calculation, we're showing a total or a resistor or anything, you write PEIR or PEIZ in AC circuits, because if you're going down, you divide, and if you go up, you multiply. Everybody remember that from first semester? Anybody not remember that from first semester? Okay, everybody says they do, but I don't believe it, but that's okay. So as long as you write this before each resistor and the totals, it'll be easier to solve, because now we know we can divide 85 by 141.4 and we can find our current, right? And we're going to go along and we're going to find a lot of different things. Oh, I don't know how I called that up, sorry. And then we're going to have another example, and I'm thoroughly past being out of time, but I want to put this example up anyway. We have 5 ohms of inductive reactance, 12 ohms. At a certain frequency, find A, the quality of the coil. Well, generally we won't be finding the quality of the coil, but the quality of the coil is going to have the same angle as the phase angle, but that's because the quality is, well, I'm not going to get into that. I don't even care about the quality. Yeah, I'm not too concerned about that. Let's get down here. And the inductance of the coil that draws 30 milliamps from 120 volt circuit at 60 cycles. What is the resistance of the coil? So now it's telling you 2 sides, and you've got to figure out, it's giving you the impedance, because if you divide the voltage by the current, you get what? The impedance. It gives you the impedance, right? So if you find the impedance and you know that the resistance of the coil is 400 ohms, what is the X sub L? So now you've got a triangle problem. We're not going to solve that just yet. We're going to talk about this a little more before the quiz next week. Tomorrow. Sorry. So, where are we? And don't panic. We're going to be practicing this stuff all semester, where we have X sub L and R and Z and some other things. Matter of fact, I think I'm going to abandon this slideshow and go down here and just add an extra slide. Let me find where I insert a slide. It's not in there, is it? Let's see. New slide. Give me a nice blank slide. Okay. Now, let me show you something real quick before. I know you guys are anxious to go, but stay calm for a minute. In the future of this class, we're going to have triangles all the time from now on. Triangles are going to become very important to you. And the angle, we always refer to as angle theta. And let's say that we have two things that have the same angle because they're the result of the same voltage and current. And we're always going to have resistance down here, and we're always going to have impedance up here, and the X sub L, or combination of X sub L plus X sub C over here. And if we take that over to a power triangle, and let's say we're multiplying up to find our total power, that's apparent power. We can find our apparent power, and apparent power always goes up here. No. And apparent power is always measured in VAs, volt amps, because the voltage times the current is the apparent power. So VAs, volts times amps, apparent power is VAs. Okay, it's nice and simple. Now, the true power is actual wattage, the actual cranking force or the actual work being done by a circuit. Okay, and then remember that pogo stick of energy that I'm wasting? Okay, that's the result of X sub L. Well, that has a power. So this is just kind of a preview, but everything we work with in this class is going to be in triangles because nothing in AC adds up directly anymore. Now you have to add up with a triangle. We're going to go over this a whole lot, so don't get in a panic if you don't know it just yet. All right? All right, let's end this one, and we'll adjourn for the day.